I'm a professor. I'm a professor at IIITM-K, and in one sentence, I'm an algorithm designer in machine learning. Of late, I've got interest in deep learning also. And to be frank, I don't work in the area of geo signal processing, but I've realized that after interacting with professors like Ram Rao, there is enormous amount of intersection between what I do and what you guys are in. So in today's session, what I intend to do is, first of all, thank you, Professor Ram Rao and team IIST for inviting me to this session. And I hope we have 90 minutes. So I'll speak for maybe like 45 to 50 minutes, and I'll share some of those experiences that I had with areas which maybe may have some sort of synergies with your work, and which may open up some research opportunities for you. And these are some of the experience that I am going to share are either with the consulting experience that I have with the corporate entities or governmental initiatives. And please don't ask me for data, because these are all what do you call privacy protected, security enabled data initiatives. But you can definitely work on some of these opportunities in public data domains also. Good, and thanks once again for for the invitation to the session. I'll share my screen. I have a PPT where what I intend to do is give you an overview of ML machine learning, the area of machine learning, and how translate to how the transition from ML to DL happens, and then connect you to some of the real opportunities and potential challenges that you will face when you actually try to use either ML or machine deep learning in your paradigm in building an application in any domain, to be very specific in geospatial domain. And I'll give some pointers to some of the initiatives or rather algorithmic interventions that you can potentially apply in your area of research, and then share some experience over the Q&A is what I intend to do. Please interrupt me. Either you can put your questions or concerns in chat, and you can always unmute, and we can chat over audio also. All right. With that, I would share my screen, and then we'll start from there. So as I already mentioned, machine learning, the journey from machine learning to deep learning, and I'm sure all of you have heard of, at least have worked on an algorithm or mechanism or an experience around machine learning to deep learning. It's all around us, and whether it's in the form of a speaker that you can return your favorite song, or in terms of a robot which has a citizenship in a country like Saudi Arabia, or it can be the chat engine that comes to your what do you call screen desktop when you log into a banking website. It's all around us, and we keep hearing about automated vehicles, cars that can fly, that can automatically detect pedestrians and stop, and things of that kind. These are all not science fiction. It's a reality around us. So AI is around us, and the question is, what is then learning? Learning has different answers. It's all about acquiring that skill to solve a problem, right? The way that humans or living beings do things. So can you exhibit capabilities of intelligence, and can you acquire that skill is learning? And it depends on your definition. Will depend on where you come from, whether you are from psychology or mathematics or neuroscience. Definition may differ a little. But all I want to say is memorization learning? That's the primary question that we ask. Yeah, this kid is learning in his online classroom, and this is a new teacher, and the kid has seen what do you call these kind of poses for the teacher. These kind of images were seen, but he can easily recognize another what do you call posture of the of the teacher and say, like, hey, this is my teacher, and he can he's not just memorizing everything that that has come in his way. Rather, he's able to find abstractions and generalize beyond what it has seen. And this is what living beings are capable of. And can we impart this kind of capability beyond memorization? Can you build abstractions beyond what you have seen? And then can use that to take decisions which exhibit characteristics of intelligence. We call it actionable knowledge or intelligence. So this particular aspect of the process of acquiring abstractions from available context of data to generalize beyond what you've seen, and that capability is called learning. And when you exhibit decision-making capabilities with that learning, or otherwise, when you exhibit decision-making capability, you say like it's intelligent. All right. So generalization is a very interesting aspect of learning, which is beyond memorization. And this is a typical context that you may have come across, where there is a lot of data, training data you have acquired from an environment. This can be as simple as, okay, this is the picture of a small building, and this is the picture of a big building, and you have a lot of tagged data for which somebody has told you that, yeah, these are all called big building pictures of big buildings and small buildings. And a learning algorithm is trying to capture the notion of big or small building and connect that to the way in which the data being described. So primarily mapping data to the label, and that abstraction is being learned, and given a new picture, it should be able to say whether it's a big building or small building with the learned model in place. And the learned model is what we call the abstraction, right? This is a typical supervised learning paradigm, and there are textbook definitions on machine learning, which says we have to, like, kind of, given the context of an experience or a context of what do you call a decision-making scenario, the program should be able to basically, with respect to a class of actions. Say, for example, you want to learn to drive a car, right? That's your problem context in hand. With the available context, you should be able to try to find an abstraction which will be able to solve the problem, and your capability to solve the problem should improve over time, and your capability should be measurable in terms of a performance measure. And when somebody says that, yes, yeah, it can be a driving test, or when you try to learn to make a cup of tea, when your mom drinks it and says, hey, this qualifies to be a tea, you say that you have learned that skill of making a cup of tea or driving a car, right? And your capability to solve that problem or find that abstraction, mental abstraction through which you can solve that problem should improve over time, and it can stop when the performance criteria that is being mentioned out there is met. So this is a classic textbook definition from a book by Mitchell in 1997. We'll go much beyond this. So let's look at a larger context of artificial intelligence, a term that Professor John McCarthy, who's with Stanford, coined maybe in 1956 in a conference in Demouth. Said artificial intelligence is all about building that intelligence capability, that decision-making capability that living beings do possess, imparting that capability to the machine or the computing machinery is artificial intelligence is all about. And there are multiple variants of definitions around it. So when you build artificial intelligence, you can build it in two ways. One is completely the rules of the game. The entire rule set is given a priori prior to you building that experience or that application. You codify everything, and then with that codified rule base, you build an experience or an application which will exhibit notions of intelligence. Right? One simple example would be you can write down all the rules in either chess or tic-tac-toe game, and then you can have a rule firing engine, and the rule firing engine is essentially a strategy with which the computer can play the game. So everything is codified. It's a priori programmed, codified sets of rules, and rules will be fired in a fashion which will look like an intelligent behavior to an external expert. And another example would be a rule-based chatbot. Most of the chatbot, I would say more than 90% of the chatbots that you see in the portals today are rule-based chatbots. They have written all the question answer pairs in fancy form in an XML. XML is it's basically a markup language. A specific form of XML is called AIML. It's an AI markup language. And what you do there is you write down all the potential questions and answers. And when you type in a question to this chatbot, what it does is it matches the question with an available question, and the best matching question would be identified, and the corresponding answer, which is already codified, there will be returned. Even what you call, to a large part of Sophia does this kind of job. So most of the available open or what you call closed source chatbots today are rule-based chatbots. So they don't do any what you call sophisticated machine learning. They all they have set of rules predefined. Another interesting what you call application of rule-based engine is called robotic process automation. I'm sure some of you must have seen it, because I mean, I also get invites from webinars and conferences across India to talk about what you call the challenges that AI faces to the primarily the workforce globally. And yeah, one of my friends was making a comment in a conference a couple of years back, saying like hundreds of computers may replace millions of jobs. Yeah, the blame is on AI, and what is that particular aspect of AI which is attracting this kind of blame. And I would say like the one that I've identified from my experience is called robotic process automation. Robotic process automation is it's essentially automating processes, soft processes in the back what we call back office context. So for example, let's take the life of an invoice processing clerk. An invoice processing clerk, her job is to get all those invoices probably over an email, and then look at those invoices and see whether the invoice is actually legal, meaning the code is actually the prices quoted is actually in accordance with the tender that was floated earlier, and does those numbers match everything, taxation, everything is in proper order, and then potentially put that into a computational spreadsheet kind of an application, and build what you call a bank statement as well as a reply to this vendor who has supplied that item, and then mail back both the vendor and the bank and say like, okay, transfer this kind of money, and tell the what you call the vendor that, okay, for supplying this number of air conditioners, your money will be credited to your bank account in this by within 3 days or whatever. This is the typical work that an invoice processing person would be doing, and automating this kind of a workflow, a soft workflow today is already done. Meaning there are software platforms where you can write simple scripts with which you can automate the entire workflow, a workflow where the human is utilizing multiple software applications to do her job. The entire workflow can be automated, and this is called RPA, or robotic process automation. And robotic process automation, and yeah, that's how it works. And a very what do you call recent enhancement to that is called cognitive robotic process automation. These are RPA applications with a cognitive edge, meaning what do you call a robotic process application which can learn from its own data. Meaning, say, essentially, there are many I don't knows. Think of a context where a program sitting at the background of a software engineer is trying to find out the patterns or the algorithmic patterns that he or she is trying to codify, and you do it for people doing similar jobs across maybe multiple computers, and beyond a point, the machine can try to write its own program, right, in depth. So these kind of things are coming up. So this is called cognitive RPA. So what I want to say is AI can be primarily built in two ways. If you have trained an Amazon Alexa, you must have seen, like, essentially you're building rules. That's one way of doing it. The next way of doing it is, can you provide it with a lot of data and let the rules or the abstractions with which it can take intelligent actions, let it be figured out by the algorithm, by the machine, and that is called machine learning based AI. Primarily, you don't provide it with explicitly programmed set of rules, rather you allow the machine to figure it out, right? So another application, another interesting context, where do we stand? I just wanted to show this because this is a Stanford question answering data set. It's a machine comprehension. Given a paragraph, can you answer a question from that paragraph? And this is a challenge, and it's an open challenge. And we have just surpassed, I would say, human performance. And AI that can answer questions from a given paragraph is still considered to be an open question. So you understand where, what is the maturity of this particular, what you call data-driven learning paradigms, right? So we have, that's where it is. And when somebody claims that Sophia is 100% machine learned, now you can imagine, it may not be not even 25-30%. All right. So there are multiple ways in which you can impart this learning capability to the machine. One is supervised learning paradigm, is primarily like teacher helps you with all the training data or all the labels, and then you learn from the teacher's experience. Right. Next is completely unsupervised. You have a lot of data, you group them together and you cluster. Say, for example, Amazon clusters their user, user market baskets, and then they come up with an algorithm called collaborative filtering. Essentially, what they do is they have clustered all the market basket data of the users, and then when a new user or a user with some items which are similar to this particular market basket clusters are coming in, they say, okay, yeah, this user has similarity to this cluster, so he has already bought these kind of items, may be able to, may be interested in buying these kind of items also. This is called, you build an implicit collaboration network among the users of that e-commerce platform. So this is called an unsupervised learning. And reinforcement learning, the best example would be the way you learn to drive a car. You get immediate feedback. You make a mistake and your instructor will pat you, will scold you and things of that kind. So you get an immediate feedback for any action. So it's essentially a state action pair. You get you do an action and you get an immediate feedback, and you improve yourself to do it better. Right, this is reinforcement learning. And the DeepMind, the program that could actually that is won over the best Go player, the AlphaGo program was built by the DeepMind engineers using reinforcement learning, a specific form of reinforcement learning called deep Q learning. Right, that's all fine. These are the different ways. These are not the only ways. There are mixes and matches of these kind of approaches. And this is a typical supervised learning paradigm. So there is a generator, there's a photographer, there is a supervisor, there is a teacher, which says a photograph is called a big building and other photograph is called a small building. And there's a learning algorithm. It should be able to compute a function parameterized by alpha. So F is a class of functions, alpha is a parameter for that class of functions, and given an X, it will take a decision. It should learn to take a decision. And if Y and if alpha X matches, we say like we have learned to achieve that task, right? You have learned to do it. So alpha is tunable and F is a class of functions, which is also decidable by certain algorithms, but every algorithm doesn't allow you to decide the class of functions over which you can build your application. So supervised learning paradigm, you have training set, you have labels, and you have VM train. So essentially the distribution that you're trying to model is available in the form of a training data set, and you find that abstraction, you find a model which tries to approximate and take a decision, right? So that's where we are, and let's look at a concrete algorithm. This is where, I mean, since I am interested in giving you, hello, am I audible?
Yes, sir.
Okay. So since I'm interested in giving you the transition from machine learning to deep learning, and since most of the research in deep learning is happening in the area of neural networks, I thought I'll give you a perspective of neural network. Hello? Hello?
Yes, sir, you're audible.
Is there a question there? I mean, I just heard.
So I can, please.
Hello?
Participant is having any question?
Go ahead, sir, please.
Okay, that's fine. Okay, so this is where all started. Perceptron is one of the early on models of neuron. So what it does is, like, I don't want to explain a lot of math out here. All it does is you have a two-class context. It was in 1957, Rosenblatt's perceptron. So all it does is it can learn a hyperplane, and the model of the neural network is shown here. Essentially, given an input, it actually like kind of it can actually, I mean, it takes a dot product with a weight vector, and so there is a linear transformation out there, and then there is a non-linearity. And in the perceptron case, it's a thresholding operation, and typical neural network case, you call that an activation. So linearity followed by non-linearity is what a typical neuron model does, and this perceptron can learn hyperplanes. So given two classes of points, you can see like plus class and the bubble classes on this particular data set. And what it does is like you can start with a random initialization of these weights, and based on the data that you see, you keep adjusting the weights using what we call a mechanism called gradient descent. Gradient descent is essentially when you make a mistake, you can look at the error curve, and you can find the gradient of the error curve. So you can compute an error by looking at those points where what you call your predicted output, it's that f alpha of x doesn't match with the desired output, the teacher provided output. By when there is a mistake, you can actually say, for example, you can take the square of the error, you can find the gradient of the function. It's a quadratic function. You can take the what you call the derivative, the first derivative, and you get dou e by with respect to w. W is essentially the parameter of this hyperplane, a hyperplane you're learning. The parameterized by w. W is essentially what you call the hyperplane is w transpose x is equal to 0. Let's assume that it's passing through the origin. And so w becomes the parameter, and your agenda is to learn w. Where you start with a random initialization of w, and then you keep adjusting w. How do you adjust w? You look at what you call, whenever you present the network with a point and the point is actually not correctly classified, what you do is you say that, okay, there is an error, and so how do I represent the error? I can represent the error as a squared error, and I can find the gradient of that function, which defines that error over the entire training data points. And then I'll say, okay, whenever there is an error, I can adjust the w in the direction where my error will come down. So I can essentially compute dou e by dou w, and with a learning parameter multiplied by a learning parameter eta into dou e by dou w, I can adjust the weight. So this is how it's called a gradient descent procedure. If somebody is interested further, I can give you more mathematical details of it. So essentially what you do here is in a perceptron is learning a hyperplane, right? And then you keep adjusting. You start somewhere and learning. You can know very well that changing that w is equivalent to rotating the hyperplane. So if you have a y-intercept wx plus c is equal to 0, what you do is you can actually push it down or pull it up, which is essentially shifting the hyperplane. So with a what you call with a parameterized form of a hyperplane such as w transpose x plus c is equal to 0, we can essentially learn the hyperplane by starting at some c and some w, and you keep adjusting whenever you make a mistake, and you stop when you have seen that they are the classes, the points belong the class are perfectly classified. And when a new point comes in, you decide whether it's on one side of the hyperplane or the other, and then you take a decision. Essentially, your decision boundary becomes a hyperplane. This is what a typical neuron does. This is what a neuron is, a capability of a neuron. And so I've already told you, this is a learning algorithm. Essentially what you do is gradient descent. You keep presenting it with patterns, with the data and the label. And when you make a mistake, you adjust the weights, right? And that's what I said, that the w, the adjustment will be eta into tx by whatever, right? It's essentially gradient. All right. So if you have a logical OR kind of a problem, logical OR is 0, 0, and will give you a 0. Everything else will give a 1. So if you have a logical OR kind of a problem, this is a linearly separable context. A hyperplane can separate the black bubble class and the white bubble classes. It'll solve the problem. Right. Beyond this, if you have a logical XOR kind of a logical XOR kind of a problem, this is not linearly separable. How do you achieve this? How do you use a neural network to solve such a problem? What you do is you combine neurons. All right. Essentially, what you do is you give the output of one neuron to other, and basically you build a network of neurons, and then this is how your brain is built. All right. And then the natural question is, how do you learn those weights? And you can use a very similar. So these kind of networks are typically called feed-forward neural networks. And you can use a very similar algorithm, similar to that of that perceptron learning algorithm. It's called delta rule. And this particular aspect, this particular algorithmic paradigm, which learns a feed forward or a multi-layer neural network, is called a backpropagation algorithm. It's essentially the same strategy. The strategy is You have training data, you present the training data. Whenever you make a mistake, you find the gradient of the error, and then you adjust, you propagate the gradient backwards till the input, and you keep adjusting the weights. It's essentially a gradient descent algorithm. It's called backpropagation. All right. Let's move on, and training is essentially about optimization. So let's look at what you call optimizing your parameters in such a way that you reduce error. So let us look at a classic neural network, a multi-layered neural network context. Right, this is a digit classification context. This is just to give you what you call the intuitions behind the multi-layered neural architecture. All right, you have multi-layered neural network. Don't worry too much about the math behind it or algorithmic paradigm. I just wanted you to give the semantics or the meaning or the conceptual understanding. All right, you present it with a digit. Digit is basically like it's represented in the form of an image. An image is given. It can take the image to have dimensions x1 to xn. So let's assume that the 64 8x8 image, 64 things out there. So when you actually have trained this neural network, or when you're training this neural network, you can see that some of the weights in each of these connections will be 1 or like closer to 1, some will be closer to 0. And if you look at it, it's equivalent to, so you give an input here, and the input gets selected and what you call get added out here. All right, this may be like low, which means that it's not. So this input may not be reaching there. This input may reach a little here. So if you look at any neuron here is essentially from the input dimension, it is choosing certain features, right? Certain dimensions, and certain dimensions are essentially discarded. And so is the case with any higher level neuron. So if you keep doing like this, hidden layers, basically like layers beyond the input point, is essentially choosing some of the features, some of the dimensions, and some others are discarded. This is what is happening. So what is the real context here? See, some of the neurons may be identifying dimensions where what you call there is a horizontal stroke in the image. Some of the what you call the neurons may be identifying there is a slightly curved things in the image. Some of the neurons may be identifying that vertical lines are in the image. Some may be identifying that there are horizontal lines in the image. And likewise, some may identify small circles in the image, and ultimately successive layers of what you call neural units. What they essentially do is they do successive layers of higher level features. So for example, given a complete textbook content without you telling like which are words, which are sentences, etc. From the characters, can the network learn words? From the words, can it learn phrases? Can it learn sentences, right? From an image, can it learn what you call a collection of basically pixel stocks, and then probably little building structures, and then lines and things of that kind, and then build and connect them together to form what you call to recognize digits. So this is essentially the capability of the higher level neuron. So essentially multiple layers are doing feature aggregations and feature specializations, and specialized features are aggregated further up in the line. And what they do is they do proper feature selection over the available data, and so they can do feature engineering, right? So this is the capability of the neural network, and your brain can also do this, right? But what happens in the literature of machine learning, if you look at it, so if you have very deep networks, doing this with a simple gradient descent approach that I just discussed, essentially what you do is find the error gradient and propagate the error backwards, was a little difficult, primarily because the gradients can either explode or can vanish over deep networks. And what deep learning, maybe like the kind of work that deep learning did, was primarily they have found ways of repositioning the algorithm, gradient descent based learning approaches in deep networks. They have figured out that yes, gradient vanishing problems can be solved, gradient exploding problems can be solved. I can push some interesting smart feature engineering before a deep network, and I can build a deeper networks. So this led to this class of algorithms which made gradient descent learning in deep networks. Deep networks, even before the deep learning came, were capable of feature, proper feature learnings from available raw data. But what happened is with the deep learning algorithms, essentially they have come up with algorithms which can make the gradient descent approaches practical in deep networks. That led to the development of deep neural networks. So essentially, they made gradient descent feasible. So that's a history, right? So what's the primary difference between a machine learning algorithm and a deep learning algorithm? There is a classic theorem in pattern recognition rather than machine learning. It's called ugly duckling theorem. Ugly duckling theorem says that you have a group of ducklings, and one of the duckling do have its beak slightly deformed. And what happens here is, unless you represent the beak of the duckling, that duckling cannot be distinguished from the rest of the ducklings as an ugly duckling, because your representation doesn't capture the aspect which is essentially considered to be ugly. All right. So you may have multiple representations of you as an individual in multiple contexts. Your bank account profile may be different from your academic profile in your institution. Will be different from your profile which you may have used in Facebook or in a matrimonial site. So you as an individual, an object getting represented in multiple ways in multiple contexts. So machine learning presumes that you have the right representation, and all that machine learning will try to do is basically, given a good representation, it'll be able to find that abstraction with which the decision making capability is built over. All right. So describing the correct abstraction or the representation for data is presumed in machine learning. If you don't have the right representation, machine learning will miserably fail. All right. So coming to deep neural networks, I've already mentioned this. Deep, what is deep? What they did is they have handcrafted network structures. Essentially, they have designed network structures which are built over known paradigms and made gradient descent approaches with which these networks can be trained. All right. And what happens in the process is they have created huge networks with millions of trainable parameters, and they made gradient based end-to-end learning practical with algorithms which are, say, they started with algorithms like the primitive versions of repositioning, backpropagation is essentially that algorithm that I was explaining on feed-forward neural networks. They came out with what is called a backpropagation through time, etc. And they said, hey, I can go beyond that. I can build algorithms like an LSTM or a GRU, which can do a better job without having these kind of issues. So, and one of the challenges they faced when they built huge networks was generalization versus overfitting. What is generalization? Primarily, I've told you it's beyond memorization. It should be able to. So given you have a training data, so the entire training data can be learned by the millions of by appropriately tuning the millions of parameters in the network, and the network can remember the entire training data. But on unseen data, the machine may not work well. So what happens here is, this is called an overfitting context. So it fits well to the training data, and it is unable to perform well in unseen data or generalization. So generalization versus overfitting was a challenge when they have built deep neural networks, which essentially does deep learning. All right, and they've come up with algorithms. I'll give you some direction to those dimensions. So classical paradigms exist in the deep DL world also. They have built supervised learning like a convolutional neural network, which is one of the most leveraged algorithmic thing in your context. That's what I could make out. And there is sequence learning mechanisms such as RNNs. Then there is unsupervised learning mechanism without a teacher, autoencoders kind of thing, RBF kind of machines, restricted RBM kind of machines, and then comes reinforcement learning. And one example would be DeepMind's DeepQ learning algorithms, which is essentially coming up. So there are many, there's a lot of resources available, primarily in the open source world in deep learning. And some of those have direct linkages, Python APIs, with which you can connect your kind of softwares like an ArcGIS to deep learning resources like a TensorFlow or a Keras, or even proprietary things like an IBM Watson. So these are all available, and you can actually build nice combinations of your own software infrastructure and with the deep learning, and you can embed your deep learning code into it. Primarily, you can connect. So, say for example, I was reading somewhere that I follow a little on ArcGIS. I was reading that ArcGIS, they do have a Python API and also a R-bridge. R is primarily that scientific computing scripting language that some of you must be using. So there are R and Python bridges, Python APIs through which you can bring in deep learning or machine learning capability to ArcGIS. All right. So let's look at some of the deep networks. Very brief. Don't worry if you don't understand math, because I don't want to tell you about maths. Recurrent neural networks. So recurrent neural networks are essentially sequential learning models. So what they do is they have an input layer, they have an output layer, and they'll have hidden layers. What is recurrent in this particular thing is they'll have connections to themselves. So hidden units will connect to hidden units. Primarily, like they'll have connections which are coming back to them. So the primary purpose of having such connections is giving it a memory. Primarily, it can learn states, and your decisions is not just based on your input. It will also depend on the current state it is in. So it's essentially when I'm talking a particular sentence, my the current word I utter will depend on the previous word, right? So or in the context of what you call, if you're tracing a road network, so you are tracing a road network, so you expect the next patch also to have a road rather than a stretch of a rivulet, right? So essentially, like there is when you are building sequential labeling or semantics over sequences, there is a need to keep what you have seen so far. The state needs to be maintained, and RNN builds that capability, has that capability in it. All right. So it's essentially like it's over time. Sequence is over time, so it can actually build states. It can essentially build states and keep remembering those states, and state information. The current input can be used to take further decisions. All right. And the learning in these structures started with, as already told you, start with backpropagation, repositioning of backpropagation, such as backpropagation through time, and then they have came up with gradient-based end-to-end learning approaches. Some of them must be known to you, called LSTMs and GRUs and all that. These are essentially switching networks, which can avoid the problem of gradient vanishing and exploding. Right, and there is a lot of computation over this gradient computation. There is a lot of overhead over the gradient computation, and they came up with a simple activation. They essentially leveraged a simple activation function called the ReLU. Is essentially max of 0, then the x. So f of x is essentially the activation computed with an x will be equal to max of 0, x, which essentially says beyond 0, fx is x. So it becomes easily computable. The gradient becomes easily it's 1. So you don't have to do any computation out there. And they have come up with learning in deep structures. One of the problems that I've already told you is they have a lot of parameters. And how do you address learning of large parameters, right? And learning of large parameters, there are two aspects of the problem. One is the computational overhead. You need a lot of compute to be done. And the other aspect is you have a lot of parameters, which means that you need a lot of data, right? They said, okay, let us address this problem by looking at very specific parts of the network, and they came up with this concept called attention. Deep learning researchers came up with this concept called attention. Attention is essentially like when we are looking at a scene, when we are looking for a particular when you are in the road and you're looking for a particular, whether some of your friend is driving through the road and you know that he's driving a car, you look only at the car. You don't concentrate on the bikes. You concentrate on the cars only, right? And see whether the car that you see in front of you is actually your friend's car. So you can actually, your visual perception is essentially around attention, and so attention over neural network is a well-researched area now. So this was like, so that you don't have to have large number of, you can concentrate on the areas where you need to concentrate on, right? And parallelization become a norm. And very recently, I would say last 2 years, they have come up with architectures where you can actually parallelize the computations for efficiency. And the architectures are called transformer architectures. And another problem is generalization versus overfitting. To address such issues, deep learning researchers came up with what is called dropouts. Dropout is essentially like you don't train every other parameters. You can randomly drop out certain weights while updating it. And then they have come out with something called batch normalization. Batch normalization is after every layer, they normalize the weights. Essentially, they do a typical mathematical normalization, statistical normalization. So they do a normalization. It is found to work. All right. So these are some of the research aspects that RNN brought in. Another interesting thing is CNN, convolutional neural network. These are essentially image processing things, and you may have seen some of those applications where a cat can be detected from can be what do you call, discriminated from a dog. So cat-dog detection problem. So essentially, what they do is they put convolutional filters. So the first step in this particular network would be you have convolutional filters, and you essentially like you think of a large image. You have a tile. It's essentially a convolutional filter. You take you compute the value from that filter, and then that value is propagated up. Essentially, you can reduce right there the computation out there in the particular network. So this is essentially feature engineering right at the beginning, and it started with all these networks such as ImageNet. So, and it drastically reduced the number of parameters, primarily because you don't take every pixel separately. You actually convolve them right in the beginning, and then you build the network further. All right. So filters are things of this kind, and what happens here is it's essentially, I mean, if you look at this equation, those who are familiar with convolution may disagree that this can't be called convolution. Yeah, I agree. That what do you call it's this particular definition of convolution. This is what convolution neural network does. It's essentially a pointwise multiplication, and this is not exactly convolution, but they call it. It's an abuse of terminology. I completely agree. And I also have a difference in opinion calling in convolution network, but they call it convolution. So essentially, they don't adhere to that particular terminology. But what it essentially does is, over an image, over a spatial signal, you can apply convolution at the beginning, and then you build a network on top of it. All right. So essentially, lower level to more macro complex level features is essentially what a convolution does. And all these convolutional filters, the weight for the convolution itself is learned using a gradient based learning algorithm. All right. And to reduce the number of parameters in convolutional network, they use operations such as max pooling. From a window, they take out only the maximum value, or average pooling, they take out the average values and things of that kind. It's essentially sampling. All right. So with all that, let me consolidate a few thoughts on learning in deep structure. All right. So we have a lot of parameters to be learned in deep learning. Locality of parameters is an issue. They said, okay, locality, see, essentially like things which are close by maybe have to be treated together. They said, hey, convolution is an interesting aspect. All right. Reusability of parameters. So learned at a previous layer may be interesting for further up. So they said, okay, yeah, all those all those similar things, let them use the same kind of kernels. All right. Same filter can be reused. So kernel reusing in convolution in a neural network is reusability. So the number of parameters can be reduced. Right, gradient based end-to-end learning, and so they essentially came out with a modular design. Say, for example, you can put convolution, then pooling, then fully connected network. So, or else you can have 3 convolution, then a pooling, things of that kind. So modularized design is something that CNN proposed, so that you can do a gradient based end-to-end modularized learning. Right, reducing computational overhead. Activation function typically used is ReLU. Large number of parameters. The convolutional network also has very similar context as that of RNN. It's called attention. Attention is possible there also. Generalization, regularization through dropout is applicable there also. Batch normalization is applicable in CNN also. All right, handcrafted networks is the norm. Structural learning through evolutionary approaches. Essentially, like, see, one of the problems with neural network is the structure of the network. Essentially, the class of functions over which you can do empirical, your data-driven parameter tuning. The structure is prefixed, meaning somebody designed the structure. The structure is handcrafted by a human, And all you can do in a neural network is you can adjust the weights based on the available data you have in hand. All right. So networks are handcrafted, and people said, hey, let's not do that. Let's do some evolutionary approaches. And there is a network called AmoebaNet, which is attempted structural learning in neural networks, which is non-trivial. Right. And don't think that deep learning is all about neural networks. I'm a researcher. I work on deep kernel machines. So we work on imparting some of these capabilities to machines like support vector machines. So I want to explain. This is my primary area of interest called statistical learning theory. Essentially, we do build machines which can do structural learning and empirical risk minimization. So what it does is essentially, like when you are building an abstraction, there are two aspects of the abstraction. One is the structure of the model, and the second aspect is choosing the right parameters for the structure. All right. Network structure in the neural network is that structure learning, and the parameter tuning is that weight learning process. Support vector machine kind of algorithms can do both. It can do structural risk minimization also. So when you are evaluating the generalization performance, your generalization performance will improve when you have the right structure and the right empirical tuning of parameters. So if you should be able to reduce the structural risk and the empirical risk. And SVM kind of algorithms can essentially do these things. But with a deep network, used to be a decade back or little more than that, SVM supported kernel machines used to has overpowered all the other machine learning paradigms in terms of their generalization capability. But with the deep network, but SVM still needs that feature engineering. See, machine learning requires that the right set of representations are given to the machine, and then the machine is able to do things. But if you don't have the right representation, you have only raw text or raw data. If you want the machine to figure out the representation, say for example, my decision has to happen over words. Say for example, your problem is as simple as deciding between a legal document and a medical document, and your representation can be character representation. Doesn't work, we know that. So the machine given these two texts should be able to figure out, a representation is at word level I am able to do this, or at a phrase level I am able to do it. But machine learning will require that you give the representation at the word level or at phrase level. But deep learning, that representation can also be the learning of the representation can also be built into the network. But current kernel machines don't have that feature learning capability. And people like us research on building that capability in the deep machines, and we have research on that dimension. So don't presume that deep learning is all about neural networks. People like us, a few researchers, even in India, we work on deep kernel algorithms, right? And I don't know whether I should tell you this, but this is an experiment with Google. You can go and check it out if you have spare time. Towards the end of the session, I can give you a context where you can just click on this particular link, and you go to experiments for google.com, where you can actually experiment with simple mechanism, AI experiments. I'll show you a very simple experiment called a teachable machine. You can launch an experiment, you can train a machine, and I'll show you how to train a machine to detect mask, right? A person with a mask. So basically, let me take an example, an image example. So teachable machine, let me take an image example. So this is what it is, and we'll come to teachable machines if there is. So essentially what you can do is, this is an image classification problem. I can demonstrate that I can, with few images which are tagged as people with mask, and other images, I think 10 images, and 10 images without mask, and I can sit in front of my video cam, and you can see that the machine is able to learn it, and you can actually download that model, that entire code in Python, TensorFlow Lite or TensorFlow, and you can use that for doing. So essentially, you can if you have images of tagged images of buildings or vehicles or things of the kind, you can build on the fly. You can build in less than 5-10 minutes. You can build models which you can either use in your application, embed in your application, in a web application or mobile application. I'll show you if there is time. in the interest of time, I'm just switching back. It's basically like launch an experiment and then we'll do that. Right. Let me move back and before I. Some relevant applications. This is something that I've come across from your domain. Applications would be like processing of satellite, aerial, or drone imagery would be interesting for you. Image classification of geo-tagged data, so you can have automated surveillance systems. So for example, I was watching some of the videos maybe like a year ago. Some of the biggest logistical problems are addressed with geospatial technologies and image processing, primarily AI. So it can be as simple as crowd monitoring and doing appropriate actions, building surveillance systems on high security areas. It can be so essentially you can say like, okay, this is a highly crowded area, so there is a classification, say crowded, medium crowded, or well crowded. Infrastructure monitoring, for example, part of the of the railroad is broken, right? You can do like kind of, there are imageries which I've read somewhere that you can even get to the precision of 7 inches, so which is highly drone imagery. So essentially what you can do is you can do classification, tagging, just like the kind of machinery that you have in place. You can do infrastructure monitoring. So we can do a lot of such things out there. Another interesting application of ML DL would be on object detection or instance segmentation. So instance segmentation is essentially what you call a precise form of object detection. So if you are detecting a dog, you can actually place the dog within a boundary box. You can say like, hey, this box has a dog, this box has a car, this box has a human. So this is object detection. And you can do object labeling also. So it's classification. And instance segmentation is essentially like if you're actually detecting an object and the exact boundaries of that. So basically a detected object of a dog will look like a dog. So you find the exact boundaries of that image. It's called instance segmentation. It's a precise form of object detection. Then another interesting thing would be called semantic segmentation. Semantic segmentation is pixel-wise classification. So for example, every pixel in image, you classify this as belonging to belonging to a green area or a raw, meaning dry land or water. So what happens is like if you want to create maps of water bodies or whatever, rivulets or road networks and things of the kind, you take an image and you try to classify every pixel in that image as belonging to water or green or whatever, or the land, bare land. And then what you can do is once you have tagged the entire pixels of that image, then you see like clearly the road can be seen and clearly the land can be separated. So these kind of things can be used for detecting encroachment, and primarily like erosions on water bodies, on land masses, or illegal encroachments to public property or water bodies, etc., can be done with this semantic segmentation kind of approaches. And that's one side of it. The other end of the game is this is primarily on imagery, and you can also do things beyond that. You can work on structured data. Say for example, you can build prediction models. You have a lot of data on contagious diseases like a COVID-19, and then can you build algorithms where you can say like, okay, I can find out implicit collaboration between points of interest, knots in a graph, and then you can build prediction models on top of it. All right, and pattern identification becomes interesting. Can you build specific patterns of propagation in a network, and then you can say, okay, this is a potentially a risky area where you should be concentrating on. Grouping, clustering is essentially node-based clustering in a graph, not clustering in a graph, or it can be like things of the kind. Collaborative filtering would be interesting on structured data. All right. So when you build, that's about the application side of it. When you build applications, what are the typical challenges that you'll face from an application designer's perspective is something that I thought I'll tell you. Infrastructure is definitely a problem. I've told you ML typically can use CPU machines, but most of the libraries on GP on the DL, deep learning world, are built over, are designed for GPU machines. GPU machines. So you need access to GPU machines to do a lot of to do a deep learning based approach. Right, application design, ML, feature engineering is your task, meaning you have the right representation, and learning models are beyond that point.
Okay.
So, hello,
Sir.
can I go ahead?
Yeah.
Oh, okay.
There are actually several questions.
Yeah, I'll wind up in another 5 minutes max.
Right.
So next thing is application design. When you're designing algorithm, ML is typically like your feature engineering. You say like, okay, this is how my features are represented. This is my data is, and then there is a classification module. There's a tagging module. There's a clustering module. There is a regression module. There is a collaborative learning module, which is on top of it. So modules are feature engineering and learning modules are can be separately treated, trained, and combined. This is what it is. And feature engineering is your job, right? You have to do it. But DL is pragmatic end-to-end learning. You don't separate out between a feature engineering and the actual decision-making capability. So that's DL. Training time and data requirements. ML can work with small training data sets. DL, since it's parameter intensive, most of the models require huge training time and data. Modality, risk minimization. ML can do both structural, I've already told you. ML can do structural and empirical risk minimization, but the structure, since neural network based DL, the structural network has to be designed by a human. The structural risk minimization is not possible with a neural architecture. But there are attempts like I've already told you, the amoeba net kind of approaches. People are attempting, but structural risk minimization, the structural complexity of the model is decided by the human. Leveraging the human capability is another aspect of it. Human helps machine learning algorithms to do feature engineering. And DL, human designs the structure primarily, like the structural complexity is decided by the human. That's where that's the difference primarily when it comes to an application design. Hype cycle says most of the AI will take another 2 to 10 years to mature. This is Gartner's hype cycle, which says that you have enough of potential out there. And with that, my slides are kind of forward. I can tell you a few applications corporate applications that I've worked on. Primarily, I'll stop sharing my screen. I can share you a few experiences. We have worked on a few consulting and governmental engagements. The first one that we have worked on is a pilferage detection context. So there was this mobile tower maintenance company. And you know that whenever power outage happens in a mobile tower, you need to fill in with diesel. Meaning there is this diesel-based generators available out there. And the company was suspecting that there are cases where people unnecessarily claim that there was a power outage and the diesel pilferage was happening. And what we have done is, like, we had data, we had put some little electronics in the tower to detect whether power was there or not. And beyond that point, we have overlaid that on the map data. We have constructed graph networks, essentially graphs over the data, and we have combined that with GIS-based data to tag paths of pilferages. Meaning, we have boiled down to people, saying that people who drive these kind of vehicles, people operate these kind of towers, these areas, these geographies are genuine. These geographies have pilferages. So this was a problem that we have addressed 3 years back, and we used classification and clustering based approaches in solving this problem. I can't give you details beyond that because we are bound by NDA, but this saved tens of lakhs of rupees for maintenance of mobile towers by a company which owns thousands of towers across India. All right, another example, experience I had with your exposure, your area of interest is dealing with data pertaining to contagious diseases. So in one district, the district collector was pretty closer to me, and so is the NHM head. So they gave us access to data. What you have done is data of the contagious diseases post monsoon. I think pre-monsoon cleaning or something. They wanted to do something around it, around data. So what we did is we have overlaid the data over the structures, over the map, and we have done algorithms similar to, we have So we construct a graph on top of it. And on the graph, we have built prediction models on edges. And we have done basic graph-based computation like a connector components. And then we were able to predict that these are areas which has potential to, and then they could use that, leverage that to take actionable intelligence. So in their action plan, they have included this model-based learnings also. So this is something that we have piloted in a district in Kerala. I think 2 years back, 2 or 3 years back. All right, that's a second application. And third application that it was essentially a consulting engagement, primarily for a company from abroad. It was primarily around what you call detection of damage or erosions in large what you call structural context, meaning buildings. They were able to, they had these drones and all that, drone imagery. So they wanted to do inspections over a geography and see like whether certain buildings are getting demolished, certain buildings are getting damaged, certain things are getting repositioned and things of that kind. So again, the problem was more of precise object detection, right? And then tagging objects. So we used mechanisms such as what you call image detection to use that. This is very recent, right? We used similar algorithms similar to CNNs. And another very recent attempt that we are going through is annotation, semantic annotation, essentially like over video frames in a video. I mean, over frames in a video. Can we tag images and say like, okay, there is this new building that's come up. There is this road which is getting what you call incrementally clogged. So can you do dynamic what you call tagging of video frames, and then can you build actionable and you should be able to interact with such videos, show me all those roads which are typically getting clogged in this kind of things, in these kind of areas. So basically this was more of an infrastructure management planning aspect for smart city engagement. So we actually like kind of started working with an agency on this kind of a context. Again, for us, the problem is semantic annotation of videos. So these are some of the experiences that I have personally on this front, which may be related to some of your research interest. And all of these are either governmental engagements or corporate engagements. And I think with that, I'll stop. I'll open up the floor for Q&A.
Yeah, thank you, Professor Asharaf. We have a lot of questions. So how do we go about is that I call out the person name. So please unmute yourself, put your question and mute them again. Okay, we start by Mr. Thomas Leonid. Please have you.
Good morning, sir.
Good morning.
Sir, for speech processing, we have to choose the CNN network or RNN network, sir.
Most of it depends on like kind of typically speech is a sequence.
Okay.
So it becomes like natural fit becomes a sequence modeling RNN. So there is no distinction. I mean, currently like you don't distinguish between the CNN and RNN when it comes to applications, but CNN is mostly for spatial processing. Sequence processing is all about RNN. So RNN kind of networks becomes the de facto choice.
Okay.
And don't think that these work in isolation. People have come out with, say for example, CRNN networks. The kind of work, the current work on semantic annotation of videos, we are actually combining CNN and RNNs. So,
okay.
So that speech is mostly to do with sequences. So RNN becomes a natural choice if you are going for a DL approach. Otherwise, it becomes the CRFs and HMMs kind of. That is a history. History is the CRF on the primarily the
past values.
Yeah, that's all kind of model, CRF models.
Thank you, sir.
So we go next is Ms. Bhargavi.
Yes, sir. Sir, what is YOLO? And this YOLO deduction model is better on TensorFlow, sir?
YOLO is essentially a framework. Yeah, there's nothing like better. It depends on the application. It's essentially a framework. I mean, so there are hundreds of frameworks out there. So YOLO, I mean, it's one of the frameworks with which you can attempt some of these algorithms out there. So I mean, I don't know whether it's better unless otherwise I see your context and data. So that's why I said, like, I mean, there is something called a no free lunch theorem, which essentially says this: there is no context independent way to say that one is better than other. So that question doesn't exist at all unless otherwise you see the context.
So next is Mr. Venkatakrishnan.
Yes, sir. Good morning, sir.
Good morning.
I am Venkatakrishnan from CMR Technical Campus, Hyderabad.
Yes.
Sir, how we can find the kernel structure from data samples?
What sort of? There are two aspects of the kernel. Are you talking about CNN? Are you talking about CNNs or are you talking about kernel machines?
Kernel machines.
Kernel machines is essentially like there are multiple approaches. One is most of the cases your conventional Gaussian kernel works.
Yes.
And
Sir.
off late people like us started working on multi-kernel approaches.
Okay, sir.
Multi-kernel is essentially like we have a pool of kernels and try to learn a weighted sum of kernels which works in your context. So multi-kernel approaches is the current norm. But if you're building a very basic application, in most of your context, a Gaussian kernel should work.
Okay. Thank you, sir.
Thank you. So next is Ms. Nayama.
Hello, good morning, sir.
Good morning.
Sir, actually, my doubt is that if I am trying to find out a particular feature from an image, I just use the HOG, histogram oriented gradient, for that one, sir. So is it possible to create the false negative, false positive, true positive in map format, sir, after the classification?
I mean, see, I don't understand your question. See, it should be possible. What we're talking about is called a confusion matrix.
Sir.
So confusion matrix is possible. I don't know what exactly your question is, but confusion matrix, any labeling context, it is possible. That's my answer. I was like, I could make out from, I may be wrong, so you are trying to do a feature engineering and then you do a labeling, right? Some sort of labeling.
Sir, there is, if for example, if it is a remote sensing satellite image, I just want to find out any particular landform that from that one, extract a particular landform.
I think it's a labeling problem. For a labeling problem, you can do that. You can do that. What you do is you have a landform, one particular form of, it's basically a forest or whatever, right? So if it's a forest or not forest, this is how you build a confusion matrix. The forest being classified as a forest is positive, true positive. Otherwise, the other one being, so basically like you do class versus the rest. That is how you build a confusion matrix. You can do that. You can build that true positives and false positives and the other way around.
So how can we mark it as a, how can we classify it in machine learning, sir? So I have got the confusion matrix as confusion matrix by using Python and all. So I don't know how to make it in map format, sir. That's my doubt. Is it possible, sir, in one of
map format in the sense, I don't know. I mean, is it something to
actually,
GIS?
After classification, I got that image as a it's a correctly classified. That means it's contouring, sir. After contouring, we got that correct false true positive as it is a true positive contour like the correct one. Otherwise, if it is the negative one, it's got in a by thresholding. We can. Is it possible to do by thresholding, sir? That's my doubt. After
what sort of classification algorithm you use?
Sir, I just use HOG for feature extraction, sir.
That's fine. For classification.
Classification, I use SVM and random forest, sir.
Okay, so SVM gives you your output, right? Basically, like it predicts you, or random forest gives you a prediction. So basically, and then from that you can get a confusion matrix. It's straightforward, right?
Yes, sir.
So I mean, I don't understand your problem. Where you get what do you call? What is your question? That's essentially the point. Say
I just want to extract the particular features. I already sir, I already mentioned that instant segmentation. You already mentioned about instant segmentation.
Okay.
I have the doubts about the instant segmentation, sir. Actually, if I'm
no, you can no. What you can do is, so essentially, okay. If your question is on instant segmentation, what you can do is you can do a pixel-wise what do you call it? Pixel-wise tagging of image. Okay, and the moment you have it, now you know everything, right? Now you know like every pixel is whether a particular landform or other.
Oh, sir.
Right. Then what you do is like, I mean, see, with your mapping, whatever, your frameworks, you should be able to plot it, right, properly.
So actually, the
You-
problem is that if I'm trying to plot it, there is one shadowing effect is happening, sir. I can't remove that one, sir. Is it any method to remove the shadow?
No, that's more of a GIS. I mean, basically technology question. I mean, if I stop at ML. I stop at ML. So I can. So if the shadowing is happening because of a confusion in the classification, I would say
sir.
like I can help you. If the
sir.
confusion, if that is the
Confusion
case,
in the classification.
then what he can do, what he can do is he can do an aggregate classification. Basically, use more than one expert. You use an SVM and RF and probably a Bayesian classifier or something like that, and you take a voting around it and take a decision. It's basically a collection of classifiers trying to classify every other pixel. This is the way in which you can approach. It's basically a committee of experts. So that's the easiest mechanism. So basically, more than one classifier for every decision, you take a voting around it. That's the easiest way to solve it.
Okay.
Thank you, Naima. We have a next question, Ms. Subha Bose.
Yes, my question is, if you have a choice of 3 platforms like MATLAB, Python, and R, which one would you prefer to implement a machine learning based on coding flexibility and implementation accuracy?
I would go for Python because most of the happenings in the open the ML DL world is around Python. And this is what I mean. See, I work with the ecosystem, the industry ecosystem, and that's the de facto standard. And R would also work if you're a little more. If you have to do a lot of statistical processing, R may be a better option, but it's more on the scientific computing world. But Python would be the best for application development. Don't go for MATLAB. Is more of what do you call it? It's laboratory experiments. It's controlled experiment.
Okay, thank you, sir.
Next is Farjana.
Good morning, sir.
Good morning.
For a beginner, which platform will be apt for learning ML?
I would say like if you want to learn ML or DL.
Sir, ML, machine learning.
Okay. Machine learning. So you learn Python, and you start working with scikit-learn. Python.
Sorry, sir, I can't hear you.
You start with Python.
Yes, sir.
And start experimenting with scikit-learn. Scikit-learn.
Okay.
Scikit-learn library, Python library. That's where you get most of the ML algorithms of them.
Okay. Thank you, sir.
Thank you, Ms. Farjana. Then next is Ms. Venkateshwar Rao, please.
Morning, sir.
Morning.
So my question is, this is related to reinforcement learning system. Are there any libraries or software tools for building the system based on the reinforcement learning, like a deep Q learning, as you mentioned?
Yeah, that's all. See, essentially, deep Q learning, there are a few GitHub repositories that I've come across, primarily on Q learning, but not much on deep Q learning. Deep Q learning is essentially the deep versions of Q learning, but there are GitHub repositories available in Q learning. Q learning. You search for GitHub Q learning implementations in Python, you get it.
And next is Shashikant.
Yeah, there are. I'm not very sure whether the new age platforms do have a plugin around it, but must be. I've never experimented with it. But Q learning implementations in Python is available.
Okay.
Q learning is the basic version of. I mean, in the most elaborate algorithm in the reinforcement learning context.
Shashikant, please.
Thank you, sir.
Good morning, sir.
Good morning.
Is it possible, sir, to forecast a groundwater modeling type forecast for if we have 20 years data? I want to forecast another 10 years data using machine learning model, whether it is possible, and we have biannual data. So is it possible, and what type of model is suitable for forecasting?
I understood. So essentially, like these are regression models with a probability needs to be predicted. But from 20 years data, predicting 10 years looks 10 years looks
No,
little
I
ambitious.
don't know. Actually, I don't have any expertise in machine learning, but we have seen lots of paper using different type of neural networks and SVR means support vector regression models to predict 5-year data and forecast another 5-year data.
It's basically a little ambitious, I would say. Primarily, like, I mean, see, it's very similar to extrapolation. See, what you do is, but you don't have that exact form of the function. What you do is do an approximation. Is what regression is all about. And the moment you do it, so all those statistical dependability parameters which you apply in a typical what you call model-driven extrapolation context applies here also. So that's why I said. So with 10 years data or 20 years data, predicting maybe 5 years data looks more sensible than a long-term prediction.
Yes. Sir, we got good result for predicting in ARIMA.
Professor Asharaf, kindly unmute yourself.
Yeah, okay, that's good. So what I want to say is, yes, you can actually, like, kind of regression models may give a little better what do you call context beyond ARIMA. What I'll say is, like, maybe a 10 years prediction you can attempt. If you're confident that ARIMA gives you a good result with 5 years, you can.
Sir, in predicting ARIMA is good. And forecasting, I don't know, sir, which model is with the best suitable, and but lots of.
Just try with SVR. SVR is like enough. If you have the right data, SVR kind of model should be able to give reasonable predictions. SVR.
Okay.
You don't have
sir.
SVR.
SVR is good. Okay. Thank you, sir.
Recently, no, long back. It was actually pending for long after getting that. Yeah, long back we had that.
Next, I call upon Giridhar to ask his question.
Sir, good morning, sir.
Good morning.
What are the advantages of the machine learning in satellite image processing?
Yeah, that's. I mean, I've right in the beginning, I've taken an excuse on this question, even though I have, like, if I'm in the. I've actually, like, collaborated a little on the national strategy body of satellite data processing, big data for GIS and all that environmental thing. I was a part of that body. So what I want to say is, I'll give you a few contexts that we were discussing. There are what I could make out from those discussions are so macro and micro parameters make sense in your context. Satellite is more of macro, and micro is more on ground, basically like ground level detection. If we can do things like when we are planning a smart city, and when you are actually deciding on the material used to construct a particular road, and if you have parameters around the kind of rains and the kind of erosions happening around it, so if we can, so there are things that you can say, like, okay, these kind of roads are typically what do you call, are getting eroded, or land bodies are getting eaten up, whatever, in 2 years time, or these roads getting damaged. So if there is actionable intelligence to be built over GIS, combining macro details with the macro information you have in satellite data. This is something that I've maybe a year back I was at Vignan Bhavan in Delhi, sitting in one of those bodies, and we were deliberating on this context. So all I want to say is applications is primarily on strategic planning, long-term planning on infrastructure. If we can combine your GIS findings and embed AI on top of it, you will be able to say, like, okay, because these kind of areas do have these kind of patterns, these kind of materials would be ideal to do these kind of things, right? And likewise, you'll be able to do things of the kind, what do you call, when you do planning for agricultural aspects. So you have data on soil, you have data on what do you call, environment, you have prediction models out there, and you have satellite data. So can you say, like, okay, so wheat cultivation, these kind of precautionary measures needs to be taken. So primarily all I want to say is building AI on top of your GIS, and with some of those macro elements being identified from the imagery of satellite data will become interesting parameters in long-term strategic planning, is what I would say, applications. That's something I have seen while deliberating with some of the biggest names in the context in India when it comes to your kind of areas.
Okay, sir. Thank you, sir.
Next, I call upon Ms. Brima to ask her question. Ms. Brima.
Good morning, sir.
Good morning.
I would like to know what is the application of ML or deep learning in data fusion, sir, satellite data fusion.
That's an interesting question. I have a PhD student working on it. So data fusion is essentially what you call combining. So the aggregation models, essentially, like, I mean, there are multiple ML approaches. So what we contextually work on aggregation of sensor networks across geographies. And you can do very similar context, similar application. You can build very similar applications in combining micro level environmental data. This is something that we have observed, where when you are combining, say, I mean, just to add continue to the earlier question, if you have to do aggregation of micro level details that you have. From the ground level observatories and things of that kind, or the drones or things of that kind. So and combining that on at a micro level, not the macro level. Micro level data fusion becomes a natural choice. So ML, we do a lot of things primarily around aggregations. These are modeling of modeling mechanisms very similar to clustering, density estimations, then prediction. I mean, essentially collaboration mechanisms, collaboration systems. These are the kind of algorithms that we use, and we also use a lot of graph-based approaches, primarily like combining conventional graph approaches and graph mining and graph aggregations. These are approaches that we are into the ML when it comes to data fusion. We also work on decision fusion, which is the next current thing.
Thank you, sir. Next, I call Raja Natarajan, sir, to ask his query.
Sir, very good morning, sir.
Good morning.
Sir, the scope of deep learning in spectral unmixing, if you have any ideas, please throw on it.
I've not worked, I mean, to be very precise, I've never worked on it, but I think IISc does some work on this context, but so can you specifically talk about a little more on the application context?
Sir, actually, we are aiming to estimate the n members and calculating the fractional abundances of converting the pixels into pure pixels.
Okay.
So particularly in multispectral and hyperspectral data imageries, we are interested in segregating or extracting features of different entities like soil, water, other kind of components. So wherein
you have enough of labeled data.
Yeah, hopefully we have enough labeled data.
I think that becomes the trivial classification problem, right? Labeling problem.
Yeah. Okay.
So I think like you can try out something like, if you have, I mean, if the data size is reasonable, I mean, not big, you can try out something like a kernel approach in the ML. That's what I would say. I would suggest attempt a simple classification approach such as an SVM based approach. Should be able to. I mean, how many classes you have?
Sir, I have about
maybe, Professor Asharaf, I think that question we can make it a little later.
Yeah, I'll write to him on the separate.
Rajan, we will answer that question a little later.
No, sir, I'll write to him and I'll get the things. Thank you.
Sure.
Thank you. Next is Mamata. So next is Ms. Mamata.
Good morning, sir. My question is like I'm doing research on synthetic aperture radar image denoising. So
Okay.
deep learning, will it be useful for denoising?
Deep learning people have attempted in the in denoising also. I think you look at the research by I think NIT. Where are you from?
Bangalore, sir.
I think KRIC do have a few people working on denoising context is what I could make out, but I don't know whether they were primarily on ML. Denoising is like kind of there are few approaches available there. I mean primarily denoising. I have not worked on it, but I've seen a few people working on it. If I remember properly, you work around you look around people in the old KRIC context, and I think there are few people out there. That's what it is. But I don't have any exposure in denoising in the DL world.
Okay, thank you, sir.
Next is Mr. Dheeraj Kumar Bera, please. Thank you. Dheeraj, are you there? Okay, so we go on. Next is Sailaja Utteda.
Good morning, sir.
Hello, sir.
Sir, my question is, can we apply machine learning techniques to WDM or OFDM? Like SVM based NLE?
Can you I mean basically like what sort of, I mean I couldn't get out the
Sir, can we apply machine learning techniques to increase the optimization of WDM, that is wavelength division multiplexing, or OFDM, orthogonal frequency division multiplexing techniques? So I have read somewhere in some of the papers that we can apply SVM based NLE, nonlinear equalizers, to increase the optimization of optical networks. So is it feasible, sir?
I mean, I see optimization is the core to SVM. So if the problem is an optimization problem, I don't know. I've not specifically worked on this, the problems that you're mentioning, but SVM is the de facto choice. SVM is built for and built over optimization techniques. If the problem is in the context of optimization, what I would suggest is, yeah, I mean the algorithms that I've seen mostly are either basically the I would say nature inspired what do you call genetic kind of algorithms or SVM kind of algorithms. SVM will definitely find a natural fit there. And another context that you may potentially look at is that what do you call the genetic algorithm based approaches, because most of the optimizers are built around what do you call evolution research approaches. So SVM also have a flavor which allows you to do optimization. So I don't know the specific problem that you're attempting, but I need more data to comment on your application. But SVM is a natural choice for many optimization problems.
And the next one is,
sir.
thank you. Yeah, thank you. Devashish Chakrabarty, please.
Yes, sir. Actually, my question is whether we can, in deep learning, how we can find the number of neurons in hidden layer.
That's the most difficult question that any DL researcher would have. See, that's why I said structural risk minimization neural network doesn't do. And all that it does is it's all about empirical tuning. So you don't, unless otherwise you have some idea on the complexity of the problem, you don't have any way to decide what do you call it. Essentially your question is around the implicit space, the feature space over which the mapping has to happen, and you have to tune it empirically. That's the only what do you call suggestion I can say. But if you have some information on the data, primarily like you know that your data falls primarily into 5 clusters, 10 clusters. So this will fall into say like, okay, I have hello.
Yes, I am listening.
So what I want to say is you may be able to like kind of build groupings around it, meaning your implicit feature space may have 5 what you call 5 dimensions, and then you move on. So it's very similar to Gaussian networks. It becomes very similar to Gaussian networks. So that's the only clue that I want to say. But some of the learnings from those Gaussian contexts were only when you have some information, semantic information on your data will become useful. Otherwise, structure is your headache.
Okay. No, some of places actually. Hello. Actually, some of the places.
Just one.
Hello.
Can I continue? So there's one more approach. That's where I said I gave some inductions on structural learning. There's something called an amoeba net. Go and look at amoeba net.
Okay.
It's essentially like it'll tell you like it's essentially it positions this problem, the problem of using the structure as an optimization problem and trying to solve that optimization problem. So there are approaches. I'm not saying like structural risk is completely out of neural network, but by default, structure is your concern. So amoeba net or GA based approaches or what do you call it, the inductions from the Gaussian kind of distributions are the only dimension